Hi and welcome. I'm trying to learn particle physics, and today the symmetry of a standard model, and after we've done it, we're gonna do standing leg stretching. And if you participate in the standing leg stretching, then it's better down. Most of the great laws of physics include some statement of conservation, implicity or explicity. Okay, Newton's first law of motion, for example, crudely states that objects in motion stay in motion, and objects at rest stay at rest. But it's nothing more than conservation of momentum, a consequence of a sort of spatial symmetry that governs the physics on top of our idealized frozen lake. No, the first thing we understand what Newton said. So Newton said, if something is in motion, it stays in motion, except the force acts upon it. And objects at rest stay at rest, except the force acts upon them. So it means conversation. The thing stays as it is. It can be moving, then it keeps moving. It can be staying, then it keeps staying. A force acting upon it can be just the air resistance. So a car comes to a stop because the air is resisting and the ground has, whatever it's called, friction, and it causes the car to stop. But otherwise the car would roll. But if there's force acting upon it. Now the next thing was here, we had here a little example, and that one says, the example was, there could be a frozen lake with ice on top of it, and there could be a puck on it, and whether the puck is on it or not, or whatever, it doesn't change the condition of the lake. And what was it now here? That was the example you mentioned. But it's nothing more than a conservation of momentum, a consequence of a sort of spatial symmetry that governs the physics on top of our idealized frozen lake. I think what I mean is, send a puck across the ice and, discounting friction, it will continue indefinitely. So what they're saying is, if the ice just goes on, and if we, what is the word for it? Discount for friction, then the ice puck just slides forever. If it wouldn't be the air resistance, or somehow stopping it. But the conservation law only holds as far as the symmetry goes. A hole in the ice will disturb the symmetry. That's interesting. Causing the puck to sink to the bottom of the lake and come to rest. But ice, I don't know what a puck is. Do you mean the ice hockey puck? I don't think that's too heavy, but I don't know. Violating Newton's first law. Okay, the symmetry can be disturbed if there's a hole in the ice and the puck goes into it and sinks down to the bottom of the lake. And then it rests there. And it violates Newton's first law. There is a force acting upon it. Is it? The whole time the gravity is working upon it, but suddenly this gravitation, it's lying on the ice, is no longer absorbed by the layer of ice, but suddenly there is no layer of ice, there's the hole, and now the gravitation takes what is it called, a puck, and sucks it down to the bottom of the lake. It isn't always obvious what is conserved and what isn't. For a long time it was assumed that mass couldn't be created or destroyed. Okay, people were believing that mass, so something existing, would I say it broadly, cannot be destroyed and not created. But Einstein's famous E = mc squared said otherwise. Matter can be created, if not out of thin air, then out of pure energy. Okay, Einstein's equation, E = mc squared, means that matter can be created out of energy. Okay, although you are made of molecules that are made of protons and neutrons, those protons and neutrons are made of quarks. Quarks, as it happens, are so light that they make up only about 1 to 2% of your body mass. The rest comes from the incredible energies with which the quarks interact. Energy has a mass? Does everything has a mass? Okay, let's read it again. The human body consists out of molecules, and they are made out of protons and neutrons. But these, as we understood it correctly in the previous part of the standard model, the protons and neutrons are consisting out of quarks. And these quarks are light. They are making just 1 or 2% of the mass. And the rest comes from the incredible energies with which these quarks interact. That means that 99% of the body weight is the energy which is interacting between the quarks. Although matter can be created from energy, energy itself in all its myriad forms adds up to a constant and permanent total. I don't understand this. Matter can be created from energy, but energy itself, in all its myriad forms, I don't know the word myriad, adds up to a constant and permanent total. Whatever. Before Nerva, so person, Emmanuel Nerva, what was it? Emmy Nerva? Before Emmy Nerva, so what she said about whatever, we haven't had it, we're gonna have it later. Before what Emmy Nerva said, so energy was simply presumed to be conserved, an assumption, so basically it became known in the 19th century as the first law of thermodynamics. So before Emily Nerva had the idea, that energy had her ideas, there was thought that energy was simply conserved. And that assumption was basic. And it was known as the first law of thermodynamics in the 19th century. But do the mathematics associated with Nerva theorem, Emmy Nerva, was it Emmy or Emily? Emmy. With Emmy Nerva's theorem, and it becomes plain that energy is conserved because of an even more basic symmetry. Specifically, that the laws of physics aren't changing with time. If they did, energy wouldn't be conserved. No, let's read it again. Before Emmy Nerva, energy was simply presumed to be conserved, an assumption so basic that it became known in the 19th century as the first law of thermodynamics. But do the mathematics associate with Nerva's theorem, and it becomes... we should do the mathematics, not the people, the mathematicians. We should do the math around it. But if you're doing the math associated with Emmy Nerva's theorem, whatever a theorem is, then it becomes plain that energy is conserved because of an even more basic symmetry. Okay, energy is conserved, it seems, but because of way more basic symmetry. It is not the symmetry whatever why. It is because specifically that the laws of physics aren't changing with time. If it did, energy wouldn't be conserved. The laws of physics are not changing. It is interesting. How? Okay, I'm not formulating this question. What Emmy Nerva's theorem adds up to is a practical prescription for making progress in physics. Identify symmetry in the world's workings, and the associated conservation law will allow you to start meaningful calculation. Okay, whatever, you have to notice something in symmetry. I mean, you can do the calculations with it. Whatever. We're going to... Is it catch on at that point? I think it's a formulation useful. Now we're going to continue at that part. If you will hear for particle physics, when you can go directly to the next part, we will continue at the position in the text. We will do now the standing leg stretching. If you participate in the standing leg stretching, then split your arm. Then bring one leg up and pointing the foot down. The mushroom. Now bring the other leg up and point the foot down. Now take the foot at the ankle, make a straight back, and bring the knee down to the floor, so to actually stretching the quad muscles. Crane. The end. Now take the other leg, and make a straight back, and bring the knee down to the floor. You want to stretch your quad muscles. Now the Grabenknoll. One heel onto the ground, pull the toes in, and move the leg from left to right. Now your other foot onto the ground, pull the toes in, move the leg from left to right. Now we're doing the train stop. The toes are pointing forward, and we're stretching the inner side of the leg. And on the other side. And now we're doing the Niagara Falls. Legs wide apart, and we're hanging down. And this is a leg stretch. So we're just hanging down. We're just breathing in through the nose and out through the mouth. Again in and out. Again in. And out we're going over to the side. And breathe in. And out over to the other side. Breathing in. And out into the middle. And we're doing the salto angelo. So bring the feet together and keep on hanging down. Breathe in. And out. Again in. And out. And another time in. And now out, we're coming slowly with a short pick up and making it the top, the backwards, short. Now we're coming to the end with a high cast hilltop stretch. Heel onto the ground, pull the toes in. Foot to the left and pull the toes in. Foot to the right and pull the toes in. Foot into the middle and move again the leg from left to right. On the other heel onto the ground, pull the toes in. Foot to the right and pull the toes in. Foot to the left and pull the toes in. To the middle and move the leg from left to right. And we're ending with a chunk united, legs wide apart. We're breathing in, coming down. Out. In. Out. And the last strong breath in. Out. Breathe in, close the legs. And out. That was still leg stretching. Thank you very much. And until next time.